So guys, what's up? I'm here to teach you something in a really short time, I think, about the half-life, right? So this was the previous talk that I was giving to you about, I think that the previous week, I think 2 weeks ago. So I'm gonna just do a short review, and we have to jump to the exercise that are related on the final exam, the final term, the final assessment, all right? So what I already told you in 11th B grade at Vermont, and this is going to be new for you, my students of 11th A, is that the half-life, it's like in this sentence, I mean in this paragraph, you can see the time that it takes for the number of unstable nuclei of an isotope in a sample to halve, or the time it takes for the initial count rate of a sample of the isotope to halve. It is different for different isotopes, of course, okay? So in this case, we have iodine 131. You can see, I'm going to point it out here, okay? I'm going to point it here that we have iodine 131, and this is a really basic example about the book in which the teachers, physics teachers around the world, we base our classes in order to prepare our students to the IGCSE exam. So right now, look at this, that in the beginning we got 40 million decaying nuclei, and remember that's an atom. In order in order to convert from a state that is unstable, okay, remember, or an isotope, to stable, in that process you can find different things, all right, like decay. In this process you're gonna have decay, and the reason that we are dealing with is that in this process it appears something about what is like the time in which the isotope, it decays to convert, to jump from an unstable to the stable state, all right? So that's, it's like, I mean, the concept of half-life is that that time in which it takes the number of an unstable nuclei of an isotope in a sample to halve. I mean, it's like in this case, right? From 40 millions, it passes to 20 million on the decaying nuclei in 8 days. So for that reasons, it's like the term half, okay? Because it's gonna be the middle, I mean the half of 40 millions, okay? So in that order, simple put, we can find that in another 8 days, it means like in 16 days, what we have here is that we have to like take the half of the 20 million at 8 days, right? So we're gonna get 10 millions. So in that order of ideas, we can find right now a kind of solution of a problem, all right? I'm gonna share with you right now this one, all right? This is really similar to one problem that you're gonna have on the final term, okay? Final term assessment. It says the graph shows how the decay rate of a radioactive source changes with time, all right? So you can see the graph that we have in the x-axis time in days, and we have in the y-axis decay rate, okay, per seconds, or decays per seconds, or decay rate, that is how many are like passing from unstable to stable, right? The number of atoms, right? In this case we have 44,000 decays per second, it says. But right now you can see that after 2 days we have, okay, here we can, I'm gonna try to, I know I can do it from in the 2 days we have in the y-axis 2000, all right? And then after 2 days, I mean other 2 days more, we have 1000, right? So in this case, let me see, I'm gonna try to take a peek and show you here in the iPad. Just hold on a second, guys, that I'm gonna try to draw it here in the iPad, because it's gonna be better for you, all right? Because I need to explain to you the y and x axis, all right? So let me just organize it. I'm gonna share with you, okay? I want to share with you the iPad. I'm gonna just to jump here. So what we have here is that, let me hold on, I want to erase this one, and I want to like do an expansion. I want to expand it, right? So we have here as this one, all right? So after 2 days, look, in 2 days we have 2,000, a count of 2,000, all right? In 4 days, I mean 2 days more after, we have 1,000. So look at the half-life between 0 and 4 days is gonna be, in 2 days I mean, it's gonna be 2,000. So if you like expand this line, this kind of graph that is in a negative exponential function, you're gonna have that at 6 days is gonna be the half of this value. So in this point it's gonna be 500, you know. And in 8 days you're gonna have, sure, you're gonna have, it's pretty easy, it's gonna be 250. All right. So the question here, it's about what will be the activity at 8 days, and of course it's gonna be 250 decays, as I already showed you that at 8 days it's gonna be 250. So it's pretty easy. This is one of the basics exercise in which you can see that you have to take the half, okay? Because I mean the count of the number of atoms, or isotopes, you have to halve it, okay? You have to like take the middle value in the same interval of days or times or seconds or whatever. Remember that it depends on the kind of isotope that you are dealing with. All right. On the other hand, we have, this is like the half-life of some isotopes. Remember that it depends on the kind, the sort of isotopes. We have 0.02 seconds for boron. We have iodine, that's 25 minutes, the half-life. I mean, after 25 minutes, you're gonna have the half of initial counting. Okay, carbon 14. Remember that we can use this one to, the carbon 14 is an isotope in which scientists, they use it for determine. I mean, to take what's the time in which dinosaurs, for instance, they were living here on Earth. And it's 5,730 years. Okay, that's the half-life. For that reason, we use carbon 14 to know like what's like the years, the time that something, I mean, it could be dinosaurs, or even the Bible, with the papers of the Bible, they found how many years it was written. So it's that for the reason, because the half-life is so long. And uranium-238, we have 4.5 times 10 to the power to 9 years. So it's a lot of years. Okay, so in this case, this is a kind of unit in which we use that is becquerel. Okay, the average number of disintegrations per second. All right, but this is just in order that you know that there is like kind of unit in order to know what's the half-life. But if just in order to know it, this was the function that I already told you, that the half-life, okay, in a Cartesian plane, in which you have in the y-axis the activity in becquerels, or maybe you can have it in the number of isotope atoms, like in this case, okay, decays per second. In the x-axis you have the times always, right? The time, it could be in days, or it could be like in this case in seconds or in minutes, right? So look at, this is the way the form of the function is an exponential, a negative exponential function. All right. So I think that forward in the lecture of math, in the mathematics course with Mauricio and I, you're gonna see this kind of function. I mean, I think that in 2 weeks later. So radioactive decay is a random process. It's really important. Okay, so this is a counting in which we can make a fit of the graph in order to get this kind of function. All right, so it's not like something that is accurate, it's a random process, it's something that you have to know. All right, this is one of the equation in order to have what's the time if you have this constant. All right, the lambda constant here, this one. Okay, lambda constant, we have that it depends on what is the the kind of isotope that they're dealing with, okay? Something that in the problem they have to give to you, but it's not, I mean, this is like advanced placement course of physics, okay? It's just like the course in the really advanced schools at North America and Canada, um, and in England, they in an advanced placement course of physics in a school, you have to see. But in this case, that is for IGCSE, you don't have to deal with these kind of equations. It's just in order that you know it, right? And okay, I'm not going to explain this one because I think that we didn't reach the topics and the level to solve this problem. But if someone wants to know how to solve it, just let me know. You can go to my office, of the teacher's office. I want to show you how to do it. But I would like that you try to do this example, okay, the fifth one, like a homework, okay, maybe for your preparation for the final test, okay. A sample for reactive isotope has an initial rate of emission of 128 counts per minute and a half-life of 4 days, right? How long will it take for the rate of emission to fall to 32 counts per minute, right? So it's the same thing, just you have to take into account that the half-life of it's 4 days, right? And the beginning of our of the counts, it was 128 counts, right? Counts per minute. Others really important I would like to show you right now. It's about what it's gonna be like. This is gonna be another one that you can see. I'm gonna do a parenthesis because in this case you have to take into account that maybe you're gonna have more counts in a detector because of the background radiation. Remember, this is really important for your final assessment. Because of the background radiation, you can have more counts that it's possible that they don't be about the half-life. I'm sorry that this was my cat that is jumping around. And take that into account, okay? Is the background radiation. You already saw it with Elmer and I, okay, about what is it, right? It's like the radiation that is not it's not getting through. I mean, it's not like the source of that radiation is not the isotope of the decays. They are background radiation that they are around the space, maybe with about stones, all right. They come from the universe, okay, and other physical I mean materials. But I would like to show you something, okay, that this is another one that you can solve it, okay. The number 13, just take a screenshot and try to solve it. But we were talking about alpha, beta, and gamma radiation, right? And it is gonna be something important. I'm just trying to find out about one problem about deflection, because you should know it about the deflection of this this is another question that you can solve 30, okay. Another kind of question that I just wanted to leave in the final term exam, but I need to do it, and I think that I have to do it here, right? So you have to know, remember, as a kind of feedback, as a kind of review, short review about the topic of decay, is that you have to remember that we have the alpha. They are particles with this configuration. They have 2 and 4, right? In beta, they have they are electrons. I mean, if they are negative radiation, okay, because you can have electrons, I mean, like particles that they have negative charge, and we can have, not in the most of the majority of the cases, not in the most that we have a positive, right, a positive charge beta, all right. But we have the gamma. It's just radiation. It doesn't have any symbol, any positive or negative symbol. So the most important thing is that if you like put magnets like with north and south pole and particles, I mean, they are like flying, like, with some kind of a speed. They are like approximating to the poles. It depends on the charge of the radiation, I mean, and of the radiation, of course. With with this of here over here, you're gonna have deflections. It's really important to know that alpha radiations, because they are positive and they obey the following equation of electromagnetism. You're gonna see in the future, I think, that the charge, the velocity, the speed, the cross product with the magnetic field. Okay, because it's positive, the deflection is gonna be in this way, right? But for negative, this is gonna be alpha. I'm gonna show you here. I'm gonna put it here, okay? But with beta, if beta, that's in the most of the cases, it's negative, it's gonna be in this way with the red one, okay? It's gonna be in this way. So right now, what do you think that is gonna be the gamma radiation? Is gonna be in a straight way, okay? In a straight path, because it doesn't have any charge, all right? So this is gonna be gamma, okay, gamma, and this is gonna be on red one, this is gonna be just beta, okay? So guys, this was, I think, all for today. This is the only thing that you should know, in order, the only topics that you needed to know to present your exam. Just try to solve the problems that I leave you here in the video, okay? Try to solve them. And in case of that you need some kind of help, just let me know. I'm gonna be really attentive to your necessities about the topics and the doubts that you can have about this exam, right? So kids, my friends, I see you around, and it was a pleasure to help you in order to prepare your exam. Bye bye.